Now let us study the cyclic structure of glucose. See, it was found that the open chain structure which we have just discussed with all the spatial arrangement of the OH groups, it was found that it was able to explain most of the properties of the glucose, but yes, there were still many properties left out which were not explained by that structure. Like the first one, the glucose doesn't give 2,4-DNP dinitrophenyl hydrazine test. It doesn't give Skiff's test, which is again a characteristic test of the aldehyde group, and it doesn't react with sodium bisulfite to form hydrogen sulfide compound. The absence of these reactions shows that it's not having free aldehyde group, whereas the open chain structure shows it is having a free aldehyde group. Another thing, when the glucose is converted to its pentaacetate, pentaester, by reacting it with acetyl chloride or acetic anhydride, when we do its acetylation, that pentaacetate product doesn't give hydroxylamine test, which again shows that there is an absence of the free CHO aldehyde group. Then another fact came out that we have actually glucose existing in two different crystalline forms, which are called alpha glucose and beta glucose. Alpha glucose is having a melting point of 419 Kelvin, whereas beta glucose is having a melting point of 423 Kelvin. Now, how they are obtained? They are obtained also differently. Though both of these are obtained from the same aqueous solution of glucose, but if the aqueous solution is concentrated and its crystallization is done at 303 Kelvin, it gives alpha glucose. But when the aqueous solution is hot and saturated and its crystallization is done at a 371 Kelvin, it leads to the formation of beta glucose. So we were not able to find out why the glucose, same molecule, is existing in two different structures, showing two different optical properties with different optical rotations, and this was clear. Later on, it was realized that glucose is not existing in an open structure. It is existing in a cyclic structure which is called pyranose structure, very similar to your pyranose molecular species. Like we know, pyranose is this type of molecular structures, a 6-membered cyclohexane ring, hexagonal ring, in which one of the atoms is oxygen, not carbon. So glucose exists in this pyranose structure. Now that is what called cyclic structure of glucose. So how glucose open chain gets converted to pyranose? Let's see this one. What happens is, see, this is the open chain structure we have for the normal glucose. Now what happens is, this carbon number 1, which is an aldehyde group, this aldehyde group shows reaction with the OH group of the 5th carbon atom, and we know from organic that the reaction of an alcohol or addition of an alcohol on the aldehyde group leads to the formation of hemiacetal. So what happens is, it can be explained like this. That this H gets what added, this shifts here, this oxygen comes here, and this H oxygen takes this H. So what happens is, ultimately this molecular species gets converted to this type of structure. With this H remains here, this double bonded O gets converted to its OH, H, third carbons, OH is on the left hand side, this is 4th, this is 5th. Now 5th and 1st gets connected to each other through a common oxygen, whereas the 6th one contains the same CH2OH. Now this is what is called the cyclic structure of your glucose, which can be written in this pyranose type of structure like this. Now this is the first carbon, second carbon, third carbon, fourth carbon, fifth carbon. See, if we put this one like this vertically, molecular species, the structure is actually put horizontal. We will get H here, OH here, H here, OH here, third one OH on above, H downward, H, OH, and fifth one is having the CH2 OH group and H on this side. Now this type, so this is what is called a cyclic structure of glucose. Now the addition of the H on this first carbon atom, which is converting the carbonyl group into an OH group, due to which the OH group on the first carbon atom can be present on the right hand side like this in this case, or it can be also on the left hand side in this case, or in the other case it can be. Now when the glucose OH group of the first carbon is on the right hand side, it's called alpha glucose, and if it is on the left hand side, it's called beta glucose. So when it is drawn in the cyclic form, this OH, in case if it is on the right hand side, comes downward, it's called alpha glucose. So if I draw the same molecular species like this, with OH is on the upward side, rest all groups on the same side. Since OH is above on the upper side, it's called what? Beta glucose. So the exact way of writing it will be alpha plus glucose. So the alpha or this beta actually gives us what? A special type of isomerism in carbohydrates, in glucose, which is due to the presence of the OH group on the first carbon atom, whether on the right hand side or left hand side, and this type of isomerism is called anomerism, and these are called anomers. So this is how we have the cyclic structures of glucose, either in the form of alpha glucose or in the form of beta glucose.